Okay, yeah, it's recording now. Okay, let's look at it one by one. Okay, maybe we do from the bottom. So let's start off with this. What year is it? So I suppose you all have already got the paper questions. Maybe I can share it to you. Okay, I suppose you all already got the exam question, so which you could actually download from our library. Okay, so anyway, I have shared it in our chat box there. So in case you haven't downloaded it, so you may get it over there. The file has been shared in the chat box. Okay, so this is 2000. Okay. 1920 semester 1. Okay, so this is for the 2019-20 semester 1. Okay, paper.
Doctor, you show,
yeah. Sorry?
Do you show your screen?
Can you guys see my screen? I supposed to have shared. I didn't share my screen.
For me, no.
Can you guys see it now?
Yeah.
Okay. So you can see my whiteboard, right? Okay, good. Okay, as usual. So I suppose everything okay. My voice okay. My screen okay. Okay. Yeah. Let's look at this one. Okay, maybe we start from the end. Okay, so question 4. So 4A, I think I could skip, right? So 4A. State without, maybe I just put it here. Okay. I think this question 1. Okay, so state the theorem. Okay, just for your information, so this was 3 years ago. Okay, this paper has been, I think, 3 years ago. Okay, so we haven't entered to the pandemic time, so that means which is still the conventional closed door written examinations. Okay, so that's why it could have a question like this: state theorems. Okay, so is fortunately or unfortunately for this time, so this is for this time will be an open book examinations, so it is not nice for us to set question like this. So that's why there's no question like this state theorems. Okay, because you can actually just copy from books, right? So forget that. So this one you may refer to the textbooks. Yeah, refer to a lecture notes. So this one is actually regarding to the so-called the Lindeberg conditions. I think so. Am I right? So which is related to this so-called the Lindeberg condition. So what is this Lindeberg condition? So which is actually just okay. Maybe I state it over here since we're going to use it later. Okay, so for every positive number epsilon. Okay, so let me just write down. Okay. So here is the condition, so-called the Lindeberg condition for every positive epsilon. Okay, I put it in this form. This is looks better. So for every epsilon, also this will be 0. So okay, this is the one. Yeah, so this is for the case whereby we assume the mean for each of the random variable is equals to 0. So this we have this. Yes. Okay, so detail. So refer to notes. Okay, lecture notes. Okay, you can see the detail for it. So I think we proceed to the next one. I think the next one is a tutorial question. Am I right? Okay, then we straight away proceed to B. Okay, question B. So this one looks familiar. Is this? Actually, yeah. This one looks familiar. So for A, so this is actually the tutorial questions. Okay, so what's the question this? So A is actually tutorial question, tutorial 5, question 6. Okay, A. Okay, so the only one different will be this, the limit part B. Okay, so then since we haven't discussed this tutorial, maybe we shall look at it. Okay. So as usual, so again, this is the hypothesis, okay, that we need to consider. First of all these random variables are independent, and secondly, so this is the one with 0 mean. So these two are the basic one. Okay, next, these two are extra. So we have this and this one. Okay, maybe I just put A and B. Okay. So show that this sequence of random variable satisfy the Lindeberg conditions. Okay, what we can do is, so we just check that to do A. So for every positive epsilon, right? So this is what we want to. We want to show the limit for this thing is equals to 0. Okay. Okay, maybe before that, so we shall look at some discussion. So put up first. Okay, before that, so let's look at our hypothesis here. So this is our variance of xi will be 1 over I, so which are not the same. So from here, then we can see directly. So we know this E of xi square. So because of mean is equal to 0, so this is actually the variance of xi square, xi, not square. Okay, so then which is equals to 1 over I. Okay. So and we use our notation. So sigma n square. So this is actually summating all the variance of xi. Okay, I running from 1 to n. So using this, so that means this is here. Okay, so this is the one. Okay, so this is a series. So from a formula in calculus, then we have this. So this is the one. Okay, so from here we can directly get, so limit n to infinity to sigma n square. So that is we're taking summating I from 1 to infinity upon I. So this is actually infinity. Okay, so so this one you have seen this before, so refer to a formula in calculus. Yeah. So this is okay series. Okay, so this is the case. Okay, so that's why please take note. So we have this picture here, or these properties. Okay, so then having this information, then we can actually solve our problem now. Okay, so this is the one. Okay, take note, this sigma n is where it's actually given as above. Okay, so this one, first of all, we can actually take out our constant. Here, so first of all, where this is equals to e of this. Okay, maybe this one we can actually bring this over there. So this is epsilon sigma n. Okay. Okay, next we have our hypothesis. Modulus of xi is less or equals to 1. So we put it inside. So then we can have this is becomes this thing will be less or equals to this. Okay, so this is because we know modulus of xi is less or equals to 1. Okay, know this. Okay, now we have used this formula quite often already. I suppose you can aware of this. So E of 1A is actually the probability of A. Yeah? So then we apply this, then we can strip away. Get this. So this one will be less or equals to, or maybe we can say this is actually not lesser. So this is actually, this will be equals to summating 1 over sigma n squared P of okay, this is the one. What else? Okay. Okay, when we come to here, so next step, then you shall recall the Markov inequality. Okay. You can remember this Markov inequality. So, which is given like this. Maybe I will change the symbol so that you can see what symbol that we should substitute there. So alpha. Supposing alpha is a positive number, P of this alpha y greater than it. So this will be less or equals to E of y. Yep. So this is the one. Okay. Okay. So this is the case over here. Okay, if you look at here, this part, right? So we can actually put this one as the square of this thing, and the square of this. Okay. So that means now we are substituting this epsilon sigma n square will be our alpha, and y will be xi squared. So using this Markov inequality, then we can see this thing will be less or equals to something 1 over sigma n, and this will become so this one we can actually bring down, so it becomes e of xi square over epsilon square sigma n square. Okay. So just for information, so in this case we are taking alpha to be epsilon square sigma n square and y to be xi square. Okay, substitute. So we got this. And it so happens, so this will be our variance. So this thing is actually equals to variance sigma n square. Okay, not really this thing. Maybe I'll put it over here. We are summating this one, e of xi. So this is actually our sigma n square. Okay, so that's why this one without I, so we can have this. So that's why this thing will become, this is a sigma n square. So then we're going to have a 1 over sigma n square, and then sigma n square over sigma n square here. Okay, so we can actually, maybe forget it, we can already put here. Okay, so we can actually cancel off these two. So this is the remaining over here. Okay, so all this amount, then we have this. This e of the whole thing. This whole thing. Okay, this whole part. Okay. Yeah, so maybe I will put it over here. Just write one more time. So this will be less than 1 over epsilon square and 1 over sigma n square. Okay. Okay, so if you put limit, taking limit to infinity for both sides. So epsilon, there's no, is independent of n, so we can take away epsilon. So then limit of 1 over sigma n square. So like what we got just now in the early beginning. So this is infinity. Okay, limit of sigma n is infinity here. Okay. So therefore, this one you can see directly. So this one will be 0. Okay, so from this one 0, then we can see hence it satisfies the Lindeberg conditions. Okay, so this is part 1. Okay, so let's look at part 2.
Dr. Lu.
Yeah.
Going back to that, from the sum to become just the constants.
Okay. Yeah. Yeah.
That again, like I can't see it because like the sigma is indexed with n as well, right? So why?
No. Because this summation involves I.
Okay.
Which means anything with I, you can't take out anything with I.
Okay, okay. So we can take out the sigma lah.
Yeah, anything without I, you could take it out. Okay, I think maybe
Yeah.
right?
Okay.
You got it?
Yeah.
So this one actually is equals to all this 1 over sigma n square. All these are considered constant, so you can take it out. Okay, now you have this one.
Okay.
Okay,
yeah.
Square. Okay, so then this one turns out to be 1 over sigma n square, 1 over epsilon square sigma n square multiplying sigma n square. So that's why this is how you get it: 1 over sigma n square, 1 over epsilon square. So you're only concerned with those with I have to remain inside the summation. So this is the case, right? So I hope this is clear. Okay, I think maybe this one shift out a little bit. Should I? A little bit better. Okay. And here. All right. So this is the case. So that's the calculation. So I next find the limiting distribution for this. Okay. So which means you want to see in the question. So this one will converge to what in distributions. Okay. So this is actually a quite straightforward already. So from our notations, so if we write as usual Sn to be this summating I xi. So and also we know this already. Sigma n square is actually equals to summating I running from 1 to n. And also, so since xi satisfy Rindberg conditions and independent. Okay, of course, with e of xi equals 0. Okay, so by the central limit theorem. Okay, so we know this. By central limit theorem, then we can make a conclusion straight away. This is summating xi over square of 1 over I. So this is actually Sn over sigma n. So this will converge in distribution to a standard normal distribution, standard normal random variables. So, okay, the next one I think I can skip because I have actually discussed this already during the lecture. Okay, I just put a question over here.
Dr. Lu?
Yeah.
The limiting distribution is about the central limit theorem, is it? First question is find the limiting distribution. So we just need to show it could be converged to some distribution either in DEP, something like that.
Oh, actually, yeah, good question. Sorry, I think good questions. It should be like this. So actually, you need to find. You need to give. Actually, you need to identify or find the capital F, the distribution function. The limits of the distribution function. Okay, that is, you want to know this limit n to infinity for f of this thing is what? Yeah, is what? So actually, this is what you want to find. When we say Sn over squared sigma n converge in distribution to a standard normal distribution, so which means, so in this question, so in these questions, okay, so it should be limit n infinity of f as n over sigma n is actually the distribution for it. Okay, maybe I would say, so this is actually the distribution function for a standard normal random variable z. Okay, so this one will be the standard function. Okay, so actually once we know the random variable for it, then we automatically know what is the distribution for this random variable. Okay, actually this is the answer, but however, if we know it is actually having the same distribution with a standard normal random variable, so automatically we can know its distribution function. Right, so yeah, it's a good question. So actually, this is what we want to know. We want to know what is this. This is the question want us to find. However, if we know the random variable, then we should know the distribution for it. Okay, so that's why when you do it up to here, then it's no, we know the answers already when you're up to here, right? Okay, I hope this is clear. Okay. Okay, so for the next one, I think I could skip. So because I have actually discussed this already during 2 weeks ago, if I'm not wrong. Okay, so this one done already. So we'll refer to lecture. Okay, job thing. I think somewhere 2 weeks ago, if I'm not mistaken. 2 weeks ago. 2 or 3 weeks ago, I can't remember. Okay, so when we're doing this, so we have already discussed this. So actually almost all are done already. So the next one, actually, we have also discussed already. So I think I could also skip this one. Okay, so for part D, I think I have also discussed this already. So this is actually tutorial 5, question 10. So this one we have discussed last week. Yeah, done in last week. So okay, you may refer back to the summary in the chopping in last week lecture. Yeah, so this is for our questions 4. Yeah. So again, let's go back to question 3. So question 3A, again, that is a question from tutorial 3. So I don't think, again, I think I have also already discussed this, so I can skip this one. So this is a question 3A. So this one, again, we have discussed this before. This one should be in tutorial 4, okay? Yeah, so done already. So that's why I don't think we need to go through it. Okay, so question 3b. This is the one. So this is something that is very much similar to the Markov inequality. We can say it is actually a Markov inequality variation of our Markov inequality. Yeah. So let's look at this. So I think the technique is quite interesting. So we look at G. This is only hypothesis. So G is a positive. Okay. Okay, positive, just to so that we can make. Okay, the most important one will be increasing. Okay. So what is meant by increasing? So that is just simply means that this thing, maybe I'll put it over here. So that means G is increasing, which means if we have a number A less or equals to B, then I'm going to G of A will be less or equal to G of B. Okay. So this is the meaning of increasing. So positive is quite important. The reason is here because of G is positive, right? So it's sort of like if a 1 over G of this is less than equals to this number, then we can actually bring this over. So if G is not positive, so the sign could be changed. Yeah, so that's why we also need G to be positive. Yeah, so this is the thing for it. Okay, so this is I think this is the most important thing for it. Okay, now we can look at it. We start solving this. Okay, so for one, so let's say epsilon is positive. Okay, let's look at this region. X, if we look at this domain, X is greater or equals to epsilon. Okay, so that means now you may assume this is epsilon, this is our X here. So that means a G of epsilon is always less or equal to G of X within this region. So that's why we just, as usual, we just consider this. Okay, okay, maybe we look at these two first. So if we put a Gx here, so Gx multiplying this indicator function. So I think for sure this is always less or equals to Gx. Okay, you can look at here. Yes, because this is actually a part of the Gx only. So we have here. Okay, next if we put a Gx here, so like I said, within this context, this domain epsilon is less or equal to X. So that means we can have G of epsilon will be less or equal to G of X. Okay, so that's why if we multiply G epsilon, so this will be always less than this. Okay, so not difficult, this thing. So in fact, I have used this technique for quite some time, many times already. Okay, next we just need to look at the first one and the last one here. Then if we combine these two, then this is what we can have: G of epsilon, one of this will be less or equals to G of X. So it's very close already. Next, what we need to do is we just need to apply the expectation value operator here. Okay, and again, So this one is a constant. So therefore we can take it out. Okay. So I think again, this is the result. We can use it quite often. E of A will be A E of X, and also we have used this already just now. E of indicator function with the event A will be P of A. So using this, so we can take out, then we can directly get this G of epsilon P of X greater or equals to. Are we taking? Okay, so will be less or equals to E of Gx. So and also because of G epsilon is positive, so then we can get this. So this one, because of G epsilon is always positive. So this is part A done. Part 1. Okay, so let's proceed to this one. I can't remember. Did I discuss this during the lecture? It looks familiar.
No idea about it.
No, right? Okay. But anyway, this is a very interesting question here. So if Ex is 0, so P of X equals 0 is equals to 1. No? I think we want X to be... Oh, okay. So I think, sorry, I didn't copy the whole question, sir. Okay, yeah, this is very important. First of all, X must be non-negative. If without a non-negative, this is not true. Okay. So this is true because of when X is always non-negative. So when Ex is 0, Px equals 0 is equals to 1. And also when Ex is finite, then the probability of X having infinity value will be equal to 0. So this is quite straightforward. Okay, what we can do is we can make use of this variation of this macro inequality. Okay? So let's look at part 2. So what we can do is we can just take G of X equals to X. So that means the identity functions. Okay? If we take G of X is equal to X, so which means, so we're going to have G of the random variable X will be random X. G of epsilon will be equals to epsilon. Okay. So what we can do is we can take epsilon to be 1 over K. So we are taking all this into this inequality, then we can see this. Hence, we have this P of X greater equals to 1 over K. Is less or equals to E of X over 1 over K. Right. So, and because of E of X is equal to 0, so this one always equals 0. Okay, so this is because of we have our hypothesis here. Okay, and next we know this. So we know if we write this, what symbol we should use? Okay, maybe we just write. Let's say we write ck to be the x greater or equals to 1 over k. So we write this to be this event. So then we know ck is increasing, okay, and limit of ck is equals to this x greater than 0. Okay, you may check one by one. Actually, what you need to just draw the line one by one. You can see it. Okay, so ck is increasing and limit of ck is equals to x greater than 0. So we know this already. So hence, p of x greater than 0, okay, is equals to limit of k to infinity of p of ck. So that is limit of k to infinity of p of x greater or equal to 1 over k. But we know this is always less equal to 0. So therefore, this one must be equal to 0. Oh, okay. Yeah, correct. Yeah, now we got it already. Okay. So we know this. The probability for x greater than 0 is 0. So hence we can see that p of x equal to 0 will be the 1 minus of this. So that is equal to 0. Equal to 1. So this is how we can get part 2. Okay, correct. Is this a question? Part 2. Okay, part 3 again. If e of x is finite, so we show that the probability of x equals to infinity is equals to 0. So in a way, from here you can say that when the expectation value for x is finite, then the value for x equals to infinity is less interest, okay, because its probability is equal to 0. So we can ignore the value whereby x is equal to infinity. So again, we just recall back our inequality. So that is, we have this inequality p of x greater or equals to infinity. Epsilon less than e of gx over g of epsilon. Okay. So we can also make use of this once again. So again, what we can do is we can take, this is part 3. So we can take g of, again, x is equal to xd identity functions. Yeah. So then we can have this same thing. So we could. Okay, again, I think we do it directly. So what's the difference? The difference will be here. Maybe just the trait. Okay, the trait for this. For this one, we are taking epsilon to be 1 over k. Okay, you see a difference. So same g, but epsilon is 1 over k. However, when we come to this, we're going to take another value for our epsilon. So we're going to take epsilon to be, it was 1 over k just now, so I'm going to take k. Okay, take this. Hence, we have this. If we look at this, then I'm going to have P of x greater or equals to k less or equals to E of x over k. Okay, so this is just E of x 1 over k. And again, bear in mind that, so this is a finite constant. So this is a finite constant. So the next thing will be we do the similar arguments for here. So what we can do is we can just simply write bk to be this event x greater or equals to k. Okay, so then we know that bk will be a decreasing sequence, and limit of bk will be x equals to infinity. Okay. So again, I think what you can do is, as usual, you can just draw some line. So b1 is x greater or equals to 1, right? So therefore, it's just like this. Okay, here. Yeah, this is 1. So b2 will be from here. 2. And b3 will be here. So that's why we got bk will be a decreasing sequence. And if you proceed, so you can see this line will go through a sort of like shorter and shorter, and at the end of the day, it will reach infinity. Okay, this is the case here. Right, so something like that. Okay, now by our theorems, then we can see that hence P of x equals to infinity will be limit of k to infinity for P of bk. So, but bk is this, so that is limit k to infinity for P of x greater or equals to k. So according to here, this will be less or equals to, because of this is a constant. Okay, so ex is a finite constant. Okay, it's a finite constant when you're taking limit for k, so which is independent of k, so you can actually take out. So 0. Okay, so just take notes here. When ex is infinity, okay, so when ex is infinity, so this value is we cannot determine. Cannot be. I mean this value. So that's why we, in order to get this result, we need to assume that this ex is a finite number. When ex is a finite number, we could have these conclusions. Yeah. So if without this assumption, so when this is infinity, so that we do not know whether this is finite or not. In fact, it is always infinity already. Yeah, we do not know the value. We cannot even determine. So that's why we want we need that hypothesis there. Okay, next one, just look at this. Okay, so let me see. Although this is not the tutorial questions, so this is actually similar to an example in the lecture. Okay, so this is actually similar to example 5.2.4 okay, in the lecture note, so you may refer to it. So in fact, the technique used here is same as the one that I use in these examples. Okay, so let's look at the question here. Again, omega is the unit interval 0, 1. As usual, we take the Borel sigma field and the standard Levet probability measure. So xn to be this 1a, an is this. So just take note for this one. So which means 1an omega is equals to 0. Why enough space? Okay, so 1an omega is 0 when omega is greater than 1 over n. Or actually omega less than 1 over n plus 1, but we do not need this. Okay. So what we consider is only this part. Okay. Either this is or either omega is greater than 1 over n, omega is less than 1 over n here. So we only need this one. Okay, let's do number 1. Okay, for omega in here. Or omega is in between 0 to 1. So what we can do is we can take an integer n such that 1 over m is less than omega. I think we can always do that. Okay, we can always take an integer. We can always take a natural number, integer m, with 1 over m less than omega. Okay, so next, when n is greater than m, so this one just simply means 1 over n is less than 1 over m. And also, this will be less than omega. Okay? So then we can have this 1 of an omega will be equal to 0. Xn of omega will be n2 or 3 of 1 an omega. So must be equals to 0. Okay, because of this must be 0, like I said, whenever omega greater than 1. So then if you take limit n to infinity, so that means will be limit n to infinity, so that will be equal to 0. And this is true for all omega, so we can see that hence limit n to infinity for xn will be equals to 0. Okay, next, this is the definitions here. This is the one. So xn converges to x if and only the probability of limit xn not equals to x is equal to 0. Okay, so if you take the complement, so this is actually equivalent to say that if and only if the probability of limit of xn equals to x is equals to 1. Okay, so here we can see a limit for xn always equals to 0. Okay, so that means this must be omega. Okay, so this one equals 0. So that means this one would imply that the event that limit xn equals to 0 will be omega. So because of this is always true, so hence we can see that. Hence, the probability of limit xn equals 0 will be always equals to 1. Okay. Actually, you can say that this is P of omega, so that is always equals to 1. So, and hence you can see that xn will converge to 0 almost surely. So let's carry on. So we have part 2 and part 3 again. Part 2 show that xn converge to 0 in L1, and after that we want to check whether xn converge in quadratic mean to 0 or not. So this one, just to record this. So when we say xn converge to x in L1, means that limit of E of this is 1, okay, xn minus x equals to 0. So in fact, this is a power of 1. Okay. So when we say xn to xn converge to x in L2, so this is just means that we're looking at the square for this, and the limit of E of this is equal to 0. So basically, we corresponding to, we refer to this number here. L2 means the square of this. Okay, L1, so power of 1. Okay, so we just need to identify the expectation value for here. So this is our xn is this. So then it is straightforward. We can do the calculations. Okay. So we can see that E of xn minus 0. Okay, so that is actually E of xn. Because of x is always non-negative, so we can put about modulus. So I think it's straightforward. That will be n3 over n. So then we take P of the probability of this. So that will be 1 over n minus 1 over n plus 1. Right? Yeah. So how was it? I think we can cancel n. So I think this is something like this, n plus 1. So then you can see this limit will be 0. So you can check easily, calculus method. So this will be 0. And so you can make conclusion xn converge to 0 in L1. So likewise, to compute part 3, we just need to calculate this expectation value. So then E of xn minus 0 squared. So that is E of xn squared. So then that is actually just when you take the square, so it will be n power of 3, 1 minus n minus this. So we're going to have a n square, n plus 1. Okay, now we got the same calculations. Let me see, limit e of xn minus 0 power of 2 will be equal to infinity. So then, so the answer is it does not converge to 0 in L2.
Sorry, Doctor.
Yeah.
Yeah, I want to ask for the part 2, right? The EXN, when we apply the expectation, right, towards the indicator function, doesn't that makes it the probability instead?
You mean this?
The EXN equals to n
This
to the
one?
power, this step, yes, in the second part.
You are right. Actually, this is the probability. This is a PAN. Okay. Just actually it's like this. There's E of xn, right? Xn, xn.
SN, I think,
Xn doesn't matter. This is simple, right? E of xn. So it will be E of n 2, 3, right?
yes.
1 of an, right? So this is a constant, so that's why we can take it out. So then P of an, and because of we are taking the standard level probability, so that's why this is just simply means the probability will be the length of the interval. Okay, so that's why this is how we can get it. So 1 over n minus this. This is how we get it. In fact, this is just the standard, so we can just get the length of the interval, and this is what we so-called the level measure. Okay.
Oh, okay.
For the next one is actually the same. The next one. Okay, the next one, I think you guys know this. If you multiply 1a, 1b will be the intersection. Okay, so we know this. We have this formula. Okay. Yeah, you just need to recall this formula. 1a, 1b is equal to 1a and b. So this is actually something in chapter 0. Okay, we have this. So that's why when we talk about xn squared, so that is so n power of 3. So and then 1an multiplied 1an. So that's why it becomes like this. Okay, so that's why then we can get it directly. E of xn squared will be, so that's why we have an n power of 3. Likewise, we can get the probability of an. So this is how we can get it. So okay, so yeah, okay, this step is it. So okay. Okay, so this is for part 2, so we can get the same thing for them. Right? Wow. Okay, so let's go back to question 2. Okay, 2a. So let's go back to our question 2. Okay, so if A, B are independent, so A, C, and B are independent. I can't remember, is this a tutorial question? But anyway, this is kind of a standard thing, sir. So just remember this. Yeah, remember this. So if A, B independent, so that means you can actually take any combination of A and A complement, B complement, any combinations, then will be, for example, then we can have A complement, B complement are independent. And also A complement, B are independent. And also A, B complement are independent. Okay, so actually all of these are independent. So you just need to take 2 of them, so then you can see it. Okay, so okay, so the proof is actually similar to it. So this one we're going to see AC. Is this? I think this could be a tutorial question, right? Okay, never mind. So let's briefly go to it, right? Okay. First of all, you just need to know this. Oh, sorry, not union. A complement and B how should I say it? So is equals to, okay, maybe you can put it this way. This one is a disjoint union A is equal to PA or B. So this one is a disjoint union. So this one disjoint. So you guys can look at the Venn diagram easily. So let's say this is A and this is B. One and the other one, I think you can see clearly. Okay. Just think about it. So then, okay, so this bit will be the complement of A and B. So this green color will be A. So then you will take out. So these two will have to be your A or B. So it's an easy question. You can just look at the diagram, you get it. So from here, then you can see P of A, C, and B plus PA is equal to PA or B. Okay, and this one is equal to PA plus PB minus PA and B. We have this formula. So here we can cancel off these two. Okay. Then the remaining is PACB is equals to PB minus PB. So this is because of from this step to this step, we are making use of the fact that AB are independent. Very close already. So this is B. And this can be put as PB. Let me put it this way. 1 minus PA multiplying PB. So that is PAC PB. So this is equal to this, then we can say, hence, these two are independent. 2B is tutorial questions. I think 2C also tutorial question, right? So do we need to discuss question 1A? So let me see this. Oh, I think I should cut. So this is actually question 1C, part 2. So X is a random variable, and F is the distributions functions. So then limit X to infinity, Fx is equal to 1. So there are two properties, right? So one properties will be like this. We know that limit X to 0 in negative infinity, Fx will be 0. So I mean you go to the end on the right hand side will be 0, and if you go to the end of the left hand side, go to the end of the right hand side is equals to 1. I don't know which one. I think I proved this in the tutorial in the lecture notes, right? So since the question here, so this one should be in lecture notes. Okay, so in this case, then we look at this one. Okay, so actually, it's not difficult to prove this. So first of all, we just need to record this. By definitions, okay, maybe we put f of n. Okay, according to the definitions, f of n is equals to p of x less or equals to n. So again, if you look at this, okay, as usual, so we just write a symbol Cn to be the event that x is less or equals to n. Okay? So then we can directly observe less than 1, less than 1, less than 2. Yeah. We do the same thing. If you draw the line, you can see the line is getting longer and longer. So Cn is increasing, and limit of Cn will be equals to so when we go when n increases, so n will be infinity. So that's why you can see this is this will end up to be the whole of the omega. Get it, right? So what you can do is you can see do it. So C1, so you begin from here, then you go to 1. So C2, you begin from here, and then you go to 2. So C3. So and you go on, then we will go to infinity. All right, it will reach infinity. So that's why when n approaches infinity, so this will be get the whole of the sample omega. So and then we can get this. So limit n to infinity for f of n equals to limit n to infinity p of cn. So that is p of omega. So this is equal to 1. Wow, we have 5 minutes left.
Can I ask
question? What question you guys want me to look at it?
I want to do one on tutorial 5.
Tutorial 5. Yeah, no problem. Tutorial 5.
Sorry, Doctor. I want to ask, can we discuss 1A2 as well?
Sorry. I was bounced up once again. So I can see your comment already.
Sorry, Doctor.
Yep.
Can we discuss 1A2 as well?
Question 1A.
Yeah, the part 2.
Question 1A. What is part 2? Question 1A. Part 2. Determine whether the events HT, HTT in independence or not. Okay.
Yeah.
Okay, so, but I think we have to go to it together, right? Okay, so make it quick. Right. Am I sharing? Sorry, I was bounced out. This is the one, right? A fair coin is total. Yes, this is the one. Okay, a fair coin is total try. So the node edge is outcome. What is the?
I think you're sharing the screen.
Sorry.
I don't think you're sharing the screen right now.
It's not sharing. Am I sharing?
Yes.
Yes.
Yeah, you can see, right? Sorry, I think something wrong with my office network today. Okay, so actually, to discuss this, we have to go to all of them, right? Okay, make it quick. So I think one, I just write out the answer is quick. So what is this actually? A fair coin is closest try. So H is the outcome head. So this is the tail suitable. Okay, as usual, this is the finite case, right? So for okay, first of all, omega, all the possible outcome will be this. Okay. So as usual, this is the finite case, right? For the finite case, we follow the standard scheme. The sigma field will be the power set. Okay, I think better don't write. I just write power set easier. Actually, by the way, how many of them are? So power set of it, yeah. So that is the power set of omega. So that means we consider all the subset to be event. Okay. So in this case, so as usual, we follow the standard scheme. So what we can do is we can just define as usual all of them. We can define the mass probability are all these to be 1 over n. Okay. So 1 over n. Okay, in this case, n is 4, so that is 1 over 4. So this is the one. So once we have defined this, yeah, this is the one. Okay, next, we want to determine whether these two are independent or not. Okay, so make it easy. We just put A to be HT, TT, B to be, I also don't know the answer, HH and TT. So A and B will be, okay, so TT. So we can see PA and B is equals to 1 over 4 P of TT. Am I right? Yes, this is P of TT, so it's 1 over 4. PA is equals to, because of two of them, right? 2 over 4, which is also equal to PB. So PA times PB is 1 over 2 times 1 over 2, so it's 1 over 4. Okay, so they are identical. So then, okay, yeah, the answer is yes, they are independent.
So doctor, for A and B, right, does it mean that each of them have two events? One, like A has HT, then B has HH, as the event?
Come again?
Like for A and B, right, does that each A or B means that each of them have two events, is it?
No. Again. Okay, so maybe I make it clear. Outcome, it means only one. How should I say?
I think two outcomes, not two events.
One element, one members of omega. Okay, so event is a collection, okay, of some outcome.
Okay, so
okay, so
that means
this is
each event
members only. So this one must be set. Okay. So now in this question, maybe let me finish first. I hope I can get it. So in these questions here, HH is an outcome. Okay,
yeah.
HS is an outcome, and so on until TT outcome. So for outcome. But when you consider A is this HH, HT, so this is event.
Oh, okay.
You get it? It's sort of like when you group several outcomes together, it could be only one outcome. If you group several outcomes together, it form an event. Get it? So it's sort of like outcome is one person. You group several person becomes an event.
Oh, okay.
Get it? Don't mess up. Yeah, of course, your group can be only one person. Okay, it's sort of like one group.
Yeah.
The group only one person. This group only one person is also considered an event, but is how should I say it? I mean, a class with only one student is also a class. Okay, something like that. Huh? I hope you can get it.
Yeah.
Don't mess up. All right. So
in this
the
case,
difference.
it's like so in this case, each event has two outcomes, is it?
Yes, exactly. You are right. Okay, it doesn't mean
Oh,
that
okay.
A is one outcome, another outcome. Got it?
Oh, okay. Yeah, got it. Yeah.
Okay.
Okay, thank you.
Okay. So question 2, go back to it. Wow, 9:34. I'm not sure whether you okay, never mind. So this is the last lecture. So maybe I will just extend a little bit. So if you feel tired, so maybe you can leave now. You can always go back to read the recorded video. Okay, so if you are still okay, so stay with me. Let's finish one more last question, question 2 of tutorial 5. Yeah. After this, we will end our lecture. So maybe I will extend for about another 10 to 15 minutes. Okay. Hey, where's my tutorial question? Just 1 minute. Tutorial 5, question 2. Oh, why question 2? Question 2. Okay, question 2. I thought my answer is clear enough. Okay.
Yeah, I don't understand the solution.
Okay, never mind. Let's go through it. Question 2. Okay, so now I go back to tutorial 5. So this is actually tutorial 5. Question 2. So actually is the idea is similar to question 1. As you guys can see, question 1 is a special case of question 2. I'm just taking R to be 1. When taking R to be 1, we go back to question 1. Yeah. Okay, so let's look at here. Question 2, we want R to be greater than 2. So this is the sequence. So xn equals to n is 1 over n. Okay, I think not the same, right? Oh, okay, not the same. Okay, show that xn converge to 0 in probability, and also determine the limit for this. Okay, so let's look at again. Okay, there are 2 parts, right? So part 1, we need to use these definitions. Okay, so when we say xn converge to random variable x in probability, if and only if what I also can't remember already. Probability will be okay. So if and only if for any positive epsilons, okay, we look at this probability. Okay, so when you bring this limit inside here, so it will becomes almost surely. Okay, so this is improper. So that means we just need to consider these probabilities only. So first of all, we need to know what is this probability. Okay. All right. Okay, so in here, again, this is a finite random variable. Okay, each of them only takes 2 values. So 2 values only when xn is either n or 0. So that means if you look at here, when we're taking x to be 0, right? So that means you can see in this case, when epsilon is positive, so that means we exclude zeros already. When epsilon is positive, so you can see this, the probability of xn minus 0 greater than epsilon. Okay. So this is just equals to the probability of xn greater than epsilon. And because of x is always non-negative, okay, we can exclude the epsilon. So this is the one. So this case, if you look at here, I mean, this is just the probability of xn equals to n. Okay, I think is it all right? So because of this is because of there are only two values only, either 0 or n. Okay, either 0 or n. So this is positive, so that means the only option will be 0. Sorry, n here. Okay, so therefore this will be equals to (1 over n power r). So if we put the limit inside, so this will be 0. Okay, so this condition is fulfilled, then we can set, hence in probability, just like that. Okay, so for the next part, we need to compute e of xn squared. So actually the technique, not the standard. So this one, we can use the standard formula to do it.
Yeah, excuse me. Doctor, yeah, I think the reason I was getting confused is because you're saying that xn can only take two values, but the way I interpret this is that xn can be any integer greater or equals to 0. Because
you mean the n?
Yeah, because xn can equals to n, and then at the side there you put n can equals to 1, 2, 3, 4, and more, right?
I don't understand what you mean.
Because you said xn can only take two values.
Yes.
But there's the n is n can be 1, 2, 3, 4, 5, 6. You know what I mean? So it's
yeah. It's like that. We have a sequence of random variable. X1 takes two value, 0 and 1. Next, X2 takes two value, 0 and 2.
Oh.
Okay, so don't confuse that. So how should I think it is quite straightforward. Maybe put it over here. So x1 is either equals to 0 or 1, and then x2 takes 2's value, 0 or 2. X3 takes two values also, and so on, just like that.
I see. Okay. Sorry.
Okay. So then this straightforward already. Okay. So that means what you need to do here, we just go back to the formula for expectation value for the discrete random variable. Okay, got it. So that's why in this case, when you goes on, xn takes 2's value or is 0 or n. Okay, so that's why when we take square, so that will be square and n square. Right, so that's why this one, it will be just 0 square multiplying the probability of x equals 0 plus another one, n square, the probability of x equals to n. So we can ignore the first case because of 0 over 0. So this one gone. So this one's what is the probabilities? 1 minus, oh, okay, so this one, 1 over n r, okay? So it is equals to n square 1 over nr. So that is oh, I think maybe this is why I want r to be greater than 2. So we have 2 of them. Okay, so if you look at 2 different cases, so look at case number 1. Okay, when r is 2, so you can see e of xn squared will be always equal to r minus r. This is 1. So that means we got the value 1 while we are taking limit. Okay, n to infinity. Right, this is the first case. So we will come to the second case when r is greater than 2. So that means this is sort of like 1 over n. That means when we take limit n to infinity for e of xn squared, so that will be 1 over n. So that will be 0. I hope this is okay.
Yeah, it makes perfect sense now. Sometimes the hardest part is understanding the question.
Oh, okay. Okay. Anything else for tutorial 5? No. Okay. So okay, so now it's 9:45 already, so we have exit 15 minutes extra. Okay, I think maybe it's a good time, so we stop our lecture now. Okay. Okay, so this will be the last lecture for the whole university, I believe so. Okay. So enjoy your holiday. Okay. So good luck. Okay. See you.